Now, there's a box in your a sidebar in this chapter that talks about meteorites, and what meteorites represent is because remember this early solar system had many planets, planetesimals, all crashing into each other. Some of those planetesimals got big enough to differentiate, and what I mean by differentiate is that the heavier elements sink to the center to form cores. So they had iron cores, whereas lighter elements rose to form the mantle or the crust of these small planets. But eventually, as they crash together, what these meteorites represent are fragments from that, right? So here we see meteorites provide clues about Earth's interior. Right? And here's some pictures of stony meteorites and iron meteorites. And what they are, they're stony and iron, and they're thought to represent fragments of planetesimals that are differentiated into mantle and core. And so obviously the iron meteorites represent the differentiated cores of these planetesimals. The stony meteorites represent the mantle material. And these are important. Usually we call these guys chondrites, and these guys are trollites. So we'll talk more about these when we use these to figure out the age of the solar system later on. And then again, Earth is a complex system. We talked about the atmosphere, the hydrosphere, the biosphere, so I've already mentioned this here. This next topic in your textbook discusses magnetism, and Earth does have a magnetic field. It has a relatively good magnetic field, and this magnetic field is important because it protects us from these dangerous solar winds that emanate from the sun, and we'll see that in a moment. So if we think about a bar magnet has a southern pole and a northern pole, and we always say that the southern pole always seeks the northern pole. So here's a line of force that goes from the south to the north. So lines of force would leave one pole, loop around, and re-enter the other pole, right? And so note that as these lines of force are looping around, they have different angles. They're very steep angles near the poles, right? But they have very shallow angles and essentially horizontal at the equator, right? So the magnetic field is like a bar magnet, right? And here they use iron fillings to show how these fields go around. And also here it says, note the north compass needle always points to the south pole in the bar magnet, right? Which is different than Earth, right? So in Earth, we can take this bar magnet, and so because we'll talk about the outer core. The outer core is actually liquid, and there are currents that develop. So because Earth spins around, these currents form, and they form a magnetic field. So the magnetic field is actually formed in Earth's outer core. But if we imagine that magnetic field to be like a bar magnet, we can see that the north pole of the bar magnet is down in the southern hemisphere, whereas the south pole is in the northern hemisphere. So that means that the lines of force leave the magnetic south pole, loop around, and re-enter the Earth at magnetic north pole, again seeking the north end, right? So always where the lines of force re-enter the Earth is always going to be the north magnetic pole, right? Another thing we should differentiate here is that note that we have a magnetic pole and a geographic pole. These are two independently different things. They're completely different. Earth rotates about the north geographic pole. That's the axis of Earth. But the magnetic pole always is fluctuating because Earth is a dynamic planet inside. Those currents are moving around. So this thing is, in fact, we have discovered that this magnetic pole fluctuates so much that it flips around over time. So in the geologic past, magnetic north was once down here near the south geographic pole, and vice versa, right? So, and it's done that numerous times. In fact, it does it on average about every 500,000 years, right? So we'll talk more about that as we go along. Now, the sun emanates these particles called solar wind. And solar wind are a series of charged particles. They can be protons, electrons, neutrons. In some cases, there are charged particles like alpha particles, which are relatively heavy. They're 2 protons and 2 neutrons, right? But these can be quite harmful if they interacted with us here on Earth. But fortunately, our magnetic field deflects those charged particles, right? Because the magnetic field will take the negative particles up toward the north pole region, magnetic pole, the positive particles down toward the south pole regions, right? And so in 1959, a scientist named by the name of Van Allen discovered that there are these radiation belts, right? And everything within this radiation belt is called our magnetosphere, right? And these are our magnetic field lines that go around the planet. So so the solar wind really kind of just we don't get the direct hit from these charged particles. And the evidence for that, and again, an evidence for magnetic force, is that we see the aurora, right? So the aurora borealis here, or northern lights or southern lights, is these charged particles are pulled toward magnetic poles, right? And when they interact with the gases in our atmosphere, they create a glow, and that glow are the auroras we see, right? Now, when we think about our atmosphere, I've already given you these numbers, but you can see that we're primarily nitrogen, then it's oxygen, and then there's other gases like carbon dioxide, methane, argon gas, right, which is less than 1% there. And then in terms of our atmosphere, basically I want you to know that our atmosphere goes up to about 100 kilometers. Literally 99.9% of our atmosphere is below 100 kilometers. Most of the action, most of the weather and climate occurs in this place called the troposphere. The troposphere is up to about 10 kilometers. And the reason there's a boundary is because temperature kind of stabilizes at the troposphere and it doesn't change for a while. And don't worry about these other ones. Just know that the stratosphere would be above the troposphere. And the other thing that we should point out here is as you go from higher in our atmosphere to lower in our atmosphere, there's going to be more pressure. It's just that the air down at sea level is under a lot more pressure because there are a lot more molecules up above it, right? So pressure decreases upward or it increases downward, right? And then the other thing we want to point out is Earth as a whole. If we look at the entire whole, which Earth, which includes the core, the mantle, and the crust, we find that it's dominated by iron and oxygen. Those are the two most abundant chemical elements in Earth, right? And I want you to differentiate that because we're going to talk about elements that are also in Earth's crust. And those are going to be important to us because we live up here, right? And so what are Earth materials is the next topic here. So organic compounds, coal, it's a rock, right? It's made from fossil fuels, from organisms that once lived on Earth, but they've been compressed and heated. So, and now they're as organic molecules there. We have minerals. In fact, the key thing about minerals is that they have an atomic order of atoms. There's a crystalline nature to them. Whereas glass, like this obsidian here, volcanic glass, is said to be amorphous. And amorphous means no shape. Remember, morph means shape. So there's no shape. So this is a natural material, but the atoms in this glass, the glass cooled so quickly that the atoms didn't have time to make a crystalline structure, right? So we'll talk more about these when we actually do minerals. We also have rocks, right? There's a variety of rocks. There's metamorphic rocks, sedimentary rocks, igneous rocks. We'll get into all those as we go along. Sediment, what is sediment? Sediment is loose material. If you took a handful of this, these particles would fall between your fingers, right? It's not a rock. You have to, this sediment has to undergo a process called lithification before it can make a sedimentary rock. And we'll discuss how that goes, how that works later on. And then metals. Metals are another earth material. The key thing about metals is that they usually conduct electricity and they're usually of high density. Some can be precious, like this gold here. And then we talk about melts and volatile materials. So gases are volatiles. Magma, you just need temperature, high enough temperature to melt rock. So think of magma as molten rock. And then in terms of the structure of the Earth, some of the early studies of Earth, especially when we determined how massive the planet was, we knew that based on the mass of the planet, the rocks that we saw up here in Earth's crust, where we could, analyze rocks up here, they were much lighter or less dense than the planet as a whole, which told scientists that the planet must have some iron inside, something very dense. In fact, initially, people thought that the core might be composed entirely of gold, right? And so, but geologists came back and said, no, it's iron. It's not as glamorous as gold. Now, we refined our ideas about the structure of Earth from earthquakes, right? Because earthquakes produce these seismic waves, these waves that travel through rocks. And we'll talk more about these as we go along. But the way these seismic waves interact with different layers within the Earth, sometimes they go faster, sometimes they go slower, tells us that there are boundaries down there. So when a seismic wave, earthquake wave that's traveling through the Earth encounters a boundary, like the boundary between the crust and the mantle, or the mantle and the core, there's a change. And we can document that change using earthquake waves or seismic waves. Now, when we look at the structure of Earth, we'll see that we have a crust, which is the outer surface of the Earth. And you find that when we look at crust, there's going to be two types. There's going to be continental crust and oceanic crust. Oceanic crust is very thin, 7-10 kilometers thick. Continental crust is about 35-40 kilometers on average. Sometimes it can be up to 70 kilometers under mountain belts. And then beneath the crust will be something called the lithosphere, or the mantle, right? In fact, there's mantle, lithosphere, and then there's mantle itself, right? So there's mantle, and the mantle can be broken up into this upper mantle and a lower mantle, the core, and then finally what I want to do here, so remember we talked about the entire Earth being mostly iron and oxygen. I want you to note that for rocks, for Earth's crust, up here where we live, the rocks we're going to study, we're going to learn about, obviously are going to be a little bit different because they're coming from material up here, either in the mantle or the crust, right? And note that the two most abundant elements are oxygen and silicon, right? So, so if we have oxygen and silicon, basically they make up 74.3% by weight of the entire crust, right, of Earth. And so I always say if you have oranges, you're going to make orange juice, right? So in this case, we have oxygen and silicon. We're going to make a mineral called a silicate mineral. So silicate minerals, those are the rock form minerals. They include quartz, a mineral called feldspar. You probably heard of olivine. You probably heard of biotite mica. All those are examples of silicate minerals. And they're really coming from magma, right? Later on, we'll talk about the different types of minerals, but note that oxygen and silicon are going to be the two most abundant in Earth's crust. When we look at tectonic plates, we want to learn about this thing called the lithosphere, right? So the lithosphere, those are the tectonic plates. And the lithosphere is kind of a combination of the upper parts of the mantle plus the crust. So when we talk about continental lithosphere, we have the continental crust plus this upper rigid part of the mantle. So think of lithos. Lithos is a Greek word which means stone, right? So the stony sphere of Earth. It includes the upper mantle, the rocky part of the mantle, and the crust. And for ocean lithosphere, it's going to be that ocean crust plus that rocky part of the mantle. All right, well, let's stop here for now.